So yesterday we left off talking about a Reimann sum, okay? A Reimann sum is when we are adding up several rectangles to approximate the area under a curve, okay? The key thing is that each rectangle may be a different width. So remember we said we could partition, okay, our x-axis into several spots. What's a partition? What does partition mean? It means wall it up or separate it out. So if there's my x-axis, I could have a partition that looks like this. So the first one's really skinny, the next one's bigger, the next one's kind of in between. A partition can be anything, okay? And then the x values that that partition corresponds to start with A, or x0. And then the next one we would call x1, the next one we would call x2, the next one we call x3, all the way up to however many we have, x in, okay, to which is the end point, B, okay? And then we can use that partition in the same kind of sum that we saw before, except now the width of each partition is different. So we have this little I, and we talked about that yesterday, okay? And our only requirement is that the CI is, take a look at this inequality. CI is between xi minus 1 and xi, okay? To make this a little concrete for you, more concrete for you here. So if this is x0, x1, x2, x3, x4, okay, C1 would be any point between x1 and x0. It could be anywhere in there. I could pick this point. I could pick x0. I could pick x1. I could pick the midpoint. I could pick any point in between x0 and x1. If I is 2, C2 is between x of 2 minus 1, so x1, and x2, so any point here, okay? All right, so that's the basic idea. This, again, our notation-wise, that's where things get tricky here. We call our partition delta, all right? And now we're going to introduce our new friend, the norm. Meet norm, the norm, okay? The norm has a very important role as we move forward. So remember, before we started with a sum like this, and what did we add in front of the sum to make it a more perfect approximation? In the previous chapter, in 4.2, we started off with sums, but then what did we do to make it perfect? It's the same process that got us from pre-calculus to calculus when we were looking at differentiation. What process is that? A limit, that's it, okay? So before we took the limit as n approaches infinity, we increased the number of rectangles in. All right, norm plays a very important role kind of like that, okay? So the width of the largest subinterval in a partition is called the norm. So the norm is the biggest delta xi, okay? Delta xi is the width of a particular part of the partition, okay? The biggest one is norm, okay? Norm's a big guy, okay? And we use this symbol to represent the norm. It's like two vertical lines on either side of our partition, okay? That is norm. Okay, and again, he is the largest width rectangle of a given partition. Okay, that's norm. Okay, the key here is that norm will determine how good our approximation is. Okay, because if you think about it, you could have a partition where you have one really big rectangle and then lots of other small ones, and you can keep making the small ones smaller. If that big one's still big, then your approximation isn't getting a whole lot better. Okay, and we'll show an example that shows that. So norm's going to be important here. One important thing to note is that if we have regular norm means that all widths are equal. So the width of every xi is always the same. And that's how the problems that we did in the previous section were all regular. The width was always the same, okay? So norm is regular when is equal to delta x equals b minus a over n. That's what we saw before, okay? So regular norm looks like that. But for a general partition, meaning the widths might vary, okay, norm has to do with how many subintervals there are, okay? In general, the more rectangles there are, the smaller norm will be. I'll say that again. The more rectangles there are, the smaller norm will be in general, okay? We can make this statement, okay, that the norm, the number of rectangles is always greater than or equal to b minus a over norm, okay? It will be equal if, looking back right up here, we rearrange this, right? If we move the norm on this side and move the n on this side, right, we get something that looks a whole lot like this. Okay, so if it's a regular partition, n will equal b minus a over the norm. But if it's not regular, meaning the widths are different, then it will be, the number of rectangles will be greater than or equal to that. Okay, so the number of subintervals in a partition approaches infinity as the norm approaches 0. So take a look at this relationship, right? If you make the norm smaller and smaller and smaller, what does that do to this whole expression? If you have something over a very small number, you would get what? A very big number. Or infinity. If it's infinitely small, then you end up with positive infinity. So in going to infinity corresponds with norm going to 0. And that, I'm sorry, this looks like an 8. I meant to write infinity. There we go. All right, so in going to infinity corresponds to the norm going to 0. Okay, so the norm goes to 0 implies, as the norm gets smaller and smaller, so as the biggest rectangle gets smaller, then the number of rectangles increases towards infinity. It is not always true the other way around. Okay. All right. This is just an example that shows that it's not true the other way around. So in this case, you're going from 0 to 1, and your first partition is a half, and then your next partition is half of that, and next is half of that, and half of that, and half of that, and half of that. You could go on infinitely smaller there, but the norm is still this guy, 1/2. The norm is the biggest partition. You could keep making smaller and smaller partitions down here, and you would have an infinite number of rectangles, but your norm is still the same. So just because you increase the number of rectangles does not make norm go to 0. But if you make norm go to 0, you force n to approach infinity. Okay. Okay, now that we've met norm, we're going to use them, okay? And we are going to introduce a very important new concept called the definite integral. Okay, if you'll remember, we looked at things called indefinite integrals. And we looked at indefinite integrals, and they look something like this. And what did we get when we did this? What's the integral of x dx? X squared what? Over 2, right?
Oh.
Plus c, okay? So x squared over 2 plus c. We got something like that. This is an indefinite integral. All right? Hold that thought, all right? We won't talk about how definite and indefinite are connected until the fun the mental theorem. But hold that thought. Let's move on to definite integrals, okay? To define a definite integral, you're going to consider this. If now we've replaced this idea of n approaching infinity with the norm approaching 0, because just as we saw before, n approaching infinity does not mean we get a better approximation necessarily. So now we have the norm approaching 0 of the sum from I equals 1 to n of f of ci times delta xi equals some number L. Who can remind me what this sum is? What kind of sum is this? There's a ci and an delta xi. Makes it a Reimann sum. Okay, Reimann sum. It's not necessarily regular. Okay. All right, so to say that this limit exists means that if we have some very small number epsilon, but that's still greater than 0, that there's another small number delta. Remember, this is from our limit definition of a limit. That for every partition, so any partition with a norm, okay, as long as that norm is greater than delta, meaning the biggest rectangle is, less than delta. So the biggest rectangle is smaller than some small number, okay, then we can set up this inequality. And this is based on the definition of a limit. So if we take the difference between these two values, it should be less than the value we get out, okay? So we picked a partition such that the norm is less than delta, okay? Then the difference between our sum here and the limit will be less than epsilon, okay? And okay, we'll stop there. Okay, this must be true. Based on our math logic, this must be true, okay? For any CI, no matter what we pick, whether it's an endpoint or midpoint or anywhere else in between. Okay, so we're going to take that and we're going to apply it one step further with a definition. Okay, so here is our official definition of a definite integral. If we have a function f on a closed interval, ab, and we know this limit exists just like what we just said, okay, then we are going to use the following notation, okay, that limit, when it's evaluated, we will use notation that says the integral from a to b, okay, the integral from a to b of f of x dx is equal to that sum, okay. So this is a whole heck of a lot of work. This limit and sum combo that we're going to learn how to do, a whole lot of work. We're going to use some new notation with our old friend, the integral symbol. Okay, looks like a curly S. A and B are the x values that are the limits of integration, meaning we go from some x value to another x value. And then f of x is whatever function that we're integrating, and dx is there, it's our differential. Note that the answer to this is not a function, but rather a number, okay? So when we evaluate a definite integral, we get a number, okay? All right. We also can say that if something is continuous, as long as a function is continuous, we can integrate it. Okay, if it's continuous, we can find the area under it. Okay, so remember, definite integration is about finding this area. Okay, all right, so let's take a look. Evaluate this definite integral. Okay, and we're going to have to refer back to our limit sum definition in just a second, but first let's make sure. Is this integrable? Well, if it's continuous, it will be integrable. And by it, I mean that function in there. F of x is 2x. Is 2x continuous from -2 to 1? Yes, it sure is. Okay, so it is integrable. All right, now we need to come up with an expression that will match our very ugly limit sum from up here. Okay, so we're looking at the limit as the norm approaches 0 of the sum from I equals 1 to 0 of f of ci times delta xi. Now, we've just made things really complicated. I'm sorry, this is the sum from 1 to in, not 0, okay? We've made things really complicated. But the truth is, we can, since mathematicians made it complicated so that it would be general enough to cover all situations. For our situation, we can make this simple, all right? And we can use a regular partition. Remind me what a regular partition is?
Rectangle that have the same width.
That's it. All the rectangles have the same width, okay? And that is b minus a over n, okay? So in our case, we can do that. Let's assume that we have a regular partition. All rectangles are the same width. In our case, b is 1, a is -2, and we're going to leave in as in, okay? So we end up with 3 over n is delta x. All right, the next task we have to tackle is what points are we going to pick? Well, what were the points that we liked to pick before for CI? Before, the easiest ones are the right endpoints, right? In general, if we start at 0, okay, then our right endpoints are delta xi. However, we don't start at 0 here. In fact, I'll sketch a graph really quick. Whoops. All right. All right, so we're finding this area. By definition, okay, a definite integral finds this limit sum, which is the area between the x-axis and the function, okay, given the limits. So we've got -2 over here, +1 over here. All right, so our right endpoints in this case will be -2 plus delta xi, or let me generalize it, it will be a plus delta xi. So in this case, it's -2 plus 3i over n, okay?
Yeah, I just not understand.
Why ci is that?
Yes.
Okay, so in general, we say it's the right endpoint.
Yeah.
Okay, and that means that we start at 0. So the first rectangle that we pick from, if we were to start at, hold on, let's look at this picture. Let's assume that we only wanted to find this area, Yua. If we only wanted to find that area, then I'm going to cut it up into 4 rectangles here. The first one would be 1/4. The next one would be 2/4, 3/4. But we're not starting there, right? We're starting over there. Okay, so that's where that -2 comes in. Exactly, exactly. So we have to start at -2 and then add our delta xi from there. Okay, now we've got the tough part done. And again, this is just making simpler choices because we know they work for this particular problem, okay? Now we have to plug it all in, okay? By definition, this notation, integral of -2 to 1, remember -2 is our lower limit, 1 is our upper limit, of 2x dx is going to be equal to the limit as the norm approaches 0 of the sum from I equals 1 to n of f of -2 plus 3i over n times delta x, which is 3 over n. Okay, now notice down here we have the limit with a norm, but there is no norm anywhere else in our expression. If it is a regular partition, the norm going to 0 coincides with n approaching infinity. right? It means the same thing if it's regular. So that means we can replace the limit as the norm approaches infinity to in approaching, we can replace the norm going to 0 with in approaching infinity, which is just like the problems we saw before, okay? So we can write it out the same way, the limit as in approaches infinity of the sum I equals 1 to n. Now we can go ahead and plug in f of x is 2 times x. So now we plug in our ci, negative 2 plus 3i over n, times 3 over n. Okay, and from there it's all simplification. Okay, so we have our limit out front. We can factor out the 2 and the 3 over n, so we have a 6 over n. And then we have our sum, negative 2 plus 3i over n. Okay, and this is where, sorry, this is an I equals 1. This is where I think we had a little confusion yesterday. So because this negative 2 is inside the sum and it's added, yes, that has to be summed up. Okay, the 6 over n, though, is a constant. It's out front. It just gets multiplied by whatever we end up with. Okay, so we are left with limit as n approaches infinity, 6 over n, of negative 2n plus 3 over n times the sum of I. Okay, the sum of I is one of the ones we memorized, n times n plus 1 over 2. Okay, and simplifying that all down, we get the limit as n approaches infinity of negative 12 plus 9 over n. This term goes to 0 when we take the limit, and we're left with negative 3. Our answer is a number. Okay, so look back what we started with notation-wise. We started with integral of negative 2 to 1 of 2x dx, and we ended up with negative 3. Okay, I know that's a lot of work. We'll see why in just a second, why that's important. Okay, so you're asking me, what does this squiggly line mean? Well, here's the key, and we'll talk more about what this means in just a second. But if our function is continuous and it is non-negative, meaning that the y values are positive, it's above the x-axis, above x-axis, okay, then the area that you are finding using this sum is exactly equal to this integral. So integral means area when it's positive and non-negative. Okay? Definite integral, I'm going to abbreviate INT, equals area when f of x is positive and continuous. Okay, so if it's non-negative, meaning it's positive y values and it's continuous, then the definite integral means area. You'll notice in the previous problem it was not non-negative. The function was negative, so it does not necessarily mean area. Okay. All right. So if that's the case, all right, then when we see this symbol, if the graph we see meets those two requirements, meaning it is continuous and non-negative, then instead of doing that big ugly sum, we can just look at the area. And there are some shapes we know how to find the area of. So let's take a look at this one. The integral from 1 to 3 of 4 dx. 4 is the function. How do you graph 4? How do you graph 4? If f of x equals 4, what does it look like? It's a horizontal line. 1, 2, 3, 4. Okay? And we're looking at integral from 1 to 3. So 1, 2, 3. Okay, we just said integral is 4 continuous and non-negative from 1 to 3. Is it continuous and non-negative from 1 to 3? Is it positive? Yes. Then this integral means area. So all we have to do, instead of doing that big sum that we just did, all we have to do is find what is this area? 8. 2 times 4. There's your answer, just like that. A lot easier than what we just saw, right? Okay. What about this next one? X plus 2. What does that look like? Okay. It's got a y-intercept at 2, right? At 1, it's 3. At 2, it's 4. At 3, it's 5, and so on. And we are looking at the integral from 0 to 1, 2, 3. There we go. Sorry, my sketch is not good. Is this function positive from 0 to 3?
Yes.
Is it continuous from 0 to 3? Okay, that means that this integral means find the area. How can we find this area? It sure is. Okay, so the area of the rectangle is 3 times 2, so 6. And what's the area of the triangle? Right, 1/2 base times height, so 3 times 2 divided by 2, so 3. The total is 9. No. Yes. No. Oh, I'm sorry, this is 3. That's a 3, not 2. Okay. So, I apologize. Ah. Oh no. Okay. We'll exit out here. All right, so this is a 3 here. So it's 1/2 3 times 3. So 9 halves. So it's 6 plus 9 halves, which is 12 plus 9 over 2, which is 21 over 2.
Oh, the same thing.
Right?
Yeah.
10.5. 10.5. Okay. All right, last one. Okay, the square root of 4 minus x squared. Anybody know what shape that is? It is a half circle with a radius of 2. Okay, it's a half circle of radius 2. All right. Is this function positive from -2 to 2?
Yes.
Okay, is it continuous?
Yes.
Then all we have to do is find the area. And so we're finding the area of a half circle of radius 2. Well, the area of a circle is what?
4 pi.
Pi r squared, right? But we're doing half of it,
Yeah.
right?
The circle.
Okay, so it's 1/2 pi 2 squared, which is
2 pi.
2 pi. That's it. Okay, so this equals 2 pi. That's the answer for that one. All right. When we get to the fundamental theorem, this will all be easier, okay? But for right now, there are 2 ways we can find definite integrals. Either painful sum, okay, which is the previous one we just did, all right, or breezy area, okay, meaning it's easy, breezy, easy area, okay? Remember, area we can only do if, what are the 2 things? Positive, if our function is positive, and if it is continuous. Okay. Okay, a couple quick properties of definite integrals. Make a star next to this because this is something that you're going to forget about and you're going to be like, oh, wait, this makes things easier, right? Okay, but you'll probably forget and have to come back to it later, okay? Important properties. First of all, if you integrate using the same limit of integration on top and bottom, so integral from a to a, so integral from 1 to 1, 2 to 2, 0 to 0, negative 500 to negative 500, if your upper and lower limits of integration are the same, then your integral equals a big fat 0, okay? That's basically like 0 area, okay? The other property is if you are taking the integral from b to a, it is just negative the integral from a to b. So that's all you do. So if you know the integral from 1 to 2 already, let's say it's 5 of some function, the integral from 2 to 1, if I'm going backwards, would be what? Negative 5. Okay? The only difference is a negative. Okay? So here are some examples. Integral from pi to pi of sine x dx would be what? From pi to pi.
0.
0. Okay, integral from the same thing to the same thing is a 0. Okay, the next one, integral from 3 to 0 of x plus 2. You will remember that we just did this, right? It was this. And what did we get for the previous problem, part 2? We got 21 over 2, right? So for this one, from 3 to 0, going backwards, what will our answer be? Negative 21 over 2. Okay, good. As again, those are quick properties. You'll forget them, make a star, you'll come back to them. Okay, another property. If you can break a function up into different intervals, then you can separate the integral. So if you assume that c is some number between a and b, it can be anywhere. Okay? If you are evaluating the integral from a to b, you can break it up into the integral from a to c and the integral from c to b and add them together. Does that make sense? So the key is that c is between a and b. Okay, so here we go. Integral from a to b, f of x dx is equal to integral a to c plus integral c to b. Okay, this is really important when it comes to absolute value. So if you take a look at absolute value functions, right, this function means when x is less than 0, it's negative x, right? And when it's x is greater than 0, it's positive x, right? So we can break this into two separate integrals, the integral from negative 1 to 0 and the integral from 0 to 1. But the function that goes in here is going to be different, right? From negative 1 to 0, it's this one, negative x dx. And then from 0 to 1, it's this one, so x dx. So we integrate and we get, well, you can't integrate yet. Okay, so we can do this graphically, right? Is it positive?
Yes.
Is it continuous?
Yes.
Okay, then we can do this. So the area is our integral. So from negative 1 to 0, what's the area?
91.
Try again.
91 half.
What is the area?
1 half.
Area is positive. It's 1/2. And what is the area from 0 to 1? Did I say negative 1 to 1? No? Did I say the wrong thing?
No, you're good.
Okay, okay. All right, so then from 0 to 1, what's the area?
From 0 to 1. 1 half.
1/2 also. All right, so together they equal, the total area is 1. Okay, so the integral of this function from negative 1 to 1 altogether is 1, but we had to do that by breaking it into pieces. Okay? Okay, last set of properties here. Similar to other things we've seen, one, we can factor out a constant. So if we have k times f of x dx, we can factor that constant out front and just deal with f of x. And if we have two functions added or subtracted inside an integral, we can break it into two separate integrals. Okay, and sometimes that's useful when thinking about it. All right, so example 6, we're given a bunch of integrals and their values to start with. So take a look at those. The integral from 1 to 3 of x squared dx is 26 over 3. That's given. We're not evaluating that. We're not deciding if that's true. They're telling us that's true. Same thing with this one. 1 to 3 of x dx is 4, and 1 to 3 of just dx is 2. Okay? So now we want to take a look at this function. All right, and apply some of our properties. What's the first property you want to think about applying to this larger function?
The plus or minus.
Yeah, we want to pull them apart. So it's going to be integral 1 to 3 of negative x squared dx plus integral 1 to 3 of 4x dx minus integral 1 to 3 of 3 dx. What's the next property we want to look at? Okay, now we need to look at the constants, because if we're looking back at what we're given here, those have no constants. All right, so this one has a negative 1 we can pull out. Okay, this one has a 4 we can pull out. And then this one has a 3 we can pull out. Now what we're left with match each of our givens exactly. Each of these integrals match each of these integrals. See how that works?
Yep.
Now we can plug in exactly our values. So this one is negative 1 times 26 over 3. This one is 4 times 4. And this one is 3 times 2, or minus 3 times 2. Okay. All right, and we add those all up and we get positive 4/3. Simple enough? All right. Last thing that we want to present today is the fact that inequalities are preserved with integrals, okay, definite integrals. So if f is integrable and non-negative, so meaning it's positive, then that integral is greater than or equal to 0. If you have another function such that that function, the original function, is less than the other function everywhere or equal to it, so f is always less than or equal to g, then that means the integral of g, okay, that inequality will be preserved when you take the integral of both sides, okay? So let me write it this way. If we start with f of x less than or equal to g of x, we can take the integral of both sides. We need our dx as notation, and we have to be going on the same limits. But whatever we do to one side, we do to the other, the inequality is preserved. And as we practice these, you'll see why that's important. Okay, that wraps it up for 4.3. Okay, we're going to do some practice today and tomorrow. We'll quiz at the end of class tomorrow. And then Monday is Fun Day, Fundamental Theorem of Calculus Day on Monday.